So I'm very happy to be here. Today, the research that I'll discuss is the work of one of my prize graduates in the state of Belanger, who's here at UAI, and I encourage you to talk to him afterwards. So much of my work over the past decade and a half has been in structured prediction, especially conditional random fields. In machine learning, there's been considerable excitement lately about deep learning, and my students and I are sharing that excitement and have been doing a lot of publishing in those areas. And this led us to wonder about the intersection between these two and what special opportunities there might be at their intersection. And that's what I'm going to talk about today. So I want to start by talking about structured prediction, not something that I need to give a tutorial on in great details in this audience, but nonetheless I want to build up some shared vocabulary, some shared visual vocabulary that we use to describe our research. And in fact, I want to start with just prediction. Like classification, logistic regression. So for example, in spam filtering, we're given a collection of email messages, and these are observed inputs X. It's our job to predict for each one of these email messages and label with spam or not spam. These will be our predicted buys. And we do this by way of these black box compatibility functions, which we call factors, which take as input the values of the variables to which they're connected and return this output some scalar compatibility or incompatibility score, which we can sum together to get an overall energy for this configuration. And the job of inference is to consider multiple options for the predicted y to find the y's that give the best energy. Here we can do this conveniently all independently of the different messages, but in different problems that have more structure, like Chinese word segmentation, we need a bit more help. So here we have a sequence of Chinese characters as input. We're trying to, for each character, predict which ones begin a word and which ones don't begin a word. And certainly the character itself is part of that compatibility function, but it's not sufficient. We can do a much better job by introducing some of these Markov factors that directly capture dependencies among the labels themselves. So we'll call this the energy that's between the whiles themselves. So we could do this with a normalized directed model, like a hidden Markov model, but not necessarily. This with unnormalized, non-reflective additional random fields and others, and all of them can be represented by factor. So the bottom part of the model has this energy and the compatibility between our observations and our predicted labels. And I usually think about this as the place where we do feature engineering, right, where we're considering, well, which facets of input X are we going to pay attention to, which will be part of this compatibility score. Maybe we'll look at neighboring variables as well, or maybe we'll introduce some latent factors, which could be helpful, or combine them on both. So when we do feature engineering, these are the kind of considerations. And this other energy among the Y's, this is what we think of as the dependency structure among the labels that we're trying to predict. And perhaps in some cases, just a first order Markov structure is enough. In other cases, maybe a second order Markov structure might be what's needed. And this kind of dependency structure of the Y shows up in all kinds of problems, including ones like multi-label document classification, in which for each label, for each document, we predict more than one label. So this document is about barley and wheat. And yes, those two co-occur quite a lot, and so it can be helpful to directly capture the dependencies among those labels. And the same shows up not just in document multi-label classification, but also for images where rows and trees occur often in the same images that can be helpful to capture the images. And in other cases, of course, we get a more complicated structure where we're predicting the labels on sub-patches of this image. All right, so when we're designing a model like this, or the dependency structure in a model like this, we're thinking about the expressivity of the dependencies to put in the dependencies we think are important for this problem. But we also need to think about the parsimony of the parameterization so that we don't create something that would be too hard to fit with the amount of data that we have. And then we also have to think about the tractability of inference. So that we don't pick a model structure that makes inference hard or often. And we might like to think that when we're picking the model, we're really mostly focused on expressivity, but all too often we're really constricted by thinking about the tractability of our prediction algorithm. And we're often actually really picking a model because it's tractable and not so much because it's really expressive in the dependencies that we want, and it's unclear which one of these two come first. So in In models that, like this, you can do sampling-based inference, or variational inference, message passing, and as long as the model doesn't get too complicated, this thing is pretty do that. All right, okay, so there's some visual language for structured prediction. Now I want to talk about deep learning. So it has its first resurgence in the 60s, and then went through a winter a little bit later, and then had a second resurgence in the 80s, when people like Jeff Hinton and Jan Kuhn were publishing in this area. They bravely continued publishing in this area during yet another winter that happened in the 1990s. I remember these days actually when the phrase neural networks appearing in your NIPS submission was actually negative, was correlated with rejection from NIPS actually. But to their credit, they kept working hard on exactly this area. And then around the early 2000s, some magic started to happen. This was when there was a breakthrough in speech recognition. Really what made modern speech recognition accurate enough to be usable as it is today, it really came thanks to deep learning. And it was around the same time that deep learning won the ImageNet competition quite decisively. And now, deep learning publications are everywhere. They completely dominate NIPS. They drastically dominated ICML, which just happened last week. There were over 3,000 people at ICML. It's pure in nature. This kind of citations per year profile is pretty typical of someone who has been working. And the world is taking notice, right? Not just the New York Times, but Facebook and Google buying DeepMind for more than $500,000. Elon Musk putting in another $1 billion into OpenAI, which is largely doing deep learning. And why is this? Well, not only because it's causing breakthroughs in building champions at the game of Go, but also because it works on real practical problems that people care about, like object recognition, where some of the latest object recognition methods using deep learning actually have superhuman performance. They're recognizing better than humans images, and even Scotch New Apple's getting on that. Okay, so how do we think about these things in relation to Bayesian networks? If you'll permit just a little bit of overgeneralization, let me lay out what I think of as sort of the landscape of this difference. So when we build Bayes networks, often we're building structures that are sparsely connected. We're designing how they're connected themselves, as opposed to deep learning, we build structures that are densely connected. Just connect everything, let learning figure out which connections matter more than others. In Bayes nets, we often hand design the representations, putting in the edges or creating variables ourselves when we know what their meaning is, whereas in deep learning, learned and distributed representations where we don't really know what the meaning of those hidden variables are, but we discover. In Bayesian networks, we're often doing loopy or iterative inference, and typically, not always. And typically, but not always in deep learning, we're doing calculating a free-form function. It's not a problem. We're cautious about capacity in Bayesian networks, whereas they're wild about high capacity. Building massive models, many billions of parameters. And maybe if we're statistically conscientious, then it's the wild west over there. And yet there's been these massive empirical successes. So, what goes on mechanically? I imagine many of you know this, but I want to set up some context. So the neural network takes the observed X at the bottom layer, real values and those, and it will predict the Y out of the top by doing some computations through these hidden layers along the way. And what does that computation look like? Well, to calculate the real value for some variable in the middle there. So that's a weighted sum of the values of the previous layer, then put through some non-linear. Where those weights are the learning parameters. So we can call this as a matrix vector product. This gives us the value of the first layer, which becomes the input into the second layer, and then the second layer becomes to the top. Like this is basically one big composed function. At the end, it's a massive, very high capacity function, and in many ways it doesn't actually matter exactly the functional form, just that it comes in layers, and then each one of the layers is differentiable with respect to the one. And then we'll train this as we usually do by having some label training data and a loss function that compares predicted output Y with the true Y, with some loss, and the loss is anything differentiable by square error and cross entropy, and then we'll do it by finding the weight that minimizes this loss by gradient descent, taking gradient steps as indicated by the class. So the key tools that enable us to use gradient descent for fitting very large neural networks are backpropagation and stochastic gradient descent, which are going to calculate gradients in just subsets of the data. And I want to talk a little bit about backpropagation. Right, so part of calculating the gradient of the loss means taking the gradient of our massive gradient function. And remember that this is a big composition of a lot of things. And it's a huge function. You take the gradient of it, you might feel nervous about this until you remember our high school calculus and the chain rule that says that, well, we're going to take the gradient of a composed function. Well, that's just the gradient of the outer function only with respect to what's on the inside, and then you just multiply that by the gradient of that inside function with respect to the initial input. And if we're building, if it's a large composed function, many compositions, that just breaks down into very simple local gradients just from one step to the next. And there aren't massive interactions throughout the entire graph. And so this means that in this composed function that we have here, we can calculate the loss at the top. That becomes a number, which we translate over to back propagation side of our calculations. And as long as we have these red partial derivatives just from one layer to the next, then we can do what we need to do. And I just want to note that having these local partial derivatives lends itself to some very nice software engineering solutions in which each of these layers becomes an object in some object-oriented system that just knows how to do a forward propagation, knows how to do its own local backward gradient. And once I build these objects, I can connect them in arbitrary ways with massive graphs. And the software engineering of how to do learning end-to-end is taken care of. Now, this is something that we don't really have in general graphical models, where we can build a graphical model, build another graphical model, and compose them together arbitrarily, and just know how to do things in so then we can backpropagate through all these layers, meaning that we can get the gradient of our loss with respect to the parameters in it, do that just by using these local partial derivative functions and these numeric gradients. And we can do this in any sort of differentiable computation graph. It doesn't have to be graphs in which each layer is doing a matrix vector product of linearity, any function from layer to layer that we differentiate, that we can differentiate. And so these can come in many different shapes, and a few popular examples. One of them are convolutional neural networks, in which our view of the input is we examine the individual little patches that may overlap or not, which share between them. And these are often used for image problems, such as digit recognition with a convolutional layer that comes in many layers and different patches. Or we can operate on sequence data, in which the output of the network at one time step also becomes the input to a top layer of the network at the next time step, and so on. And these can be feed forward in one direction, or also can both feed forward and feed backward at the same time without controllable predictions at the time step. This is an example. Examples of recursive neural networks are LSTMs, GNUs, and linear plots. So, just an example of a real-world neural network. Google's 2014 ImageNet competition entry, 24 layers, was trained on many machines at once, and can take images like this and recognize them both as a medial, they're both quite different, and also can be quite specific about its predictions of success for recognizing these different kinds of flowers. And the real power of deep learning is coming from its ability to learn very rich representations of the input. At the bottom layers, learning patches that capture edges, different oriented edges, and then the upper layers compose together to form little patches that represent eyes, or car wheel wells, or noses, etc. And then upper levels recognizing, representing entire faces, or cars, or and then some of more. When it's the bell, we can use the neural network's knowledge or preference for certain kind of patches to have a sense of artistic style. Here's a case in which we give as input a photograph, an example of a painting by Van Gogh, the neural network will learn to prefer patches that look somewhat like this, and it can re-render your photograph in the artistic style. Again, we'll come back to this later as well. All right, so summarizing here, the key ingredients for deep learning are that we represent, that we're doing representation learning that happens in layers that allows us to build these massively high-capacity models. That we can do auto-differentiation through many layers with these local gradients that supports gradient assignments in layers, and it's easy to engineer complex models in this object-oriented fashion. And that we can train these, now that we have these massive capacity models, that we can train them on very big data by using GPU hardware acceleration. All right, but what about structure prediction? We didn't talk about that at all. This is what we've described so far as a feed-forward computation that at each layer is making independent predictions of each one of the nodes in a particular layer. We talked about learning the rich representations of the inputs, but not representations of the output. And so this leads to real body of the talk. We've talked about background and structured prediction and deep learning independently, and now I want to cover 4 facets of their intersection and how they relate to each other, culminating in some new work that David and I are very excited about that I'll describe at the end. So the first version is the simplest of all. Basically, is what we've been talking about so far, using deep networks to encode the input features, but then making independent prediction at the end, just by feed-forward inference. It just turns out that by capturing this very rich layered structure, you can often successfully solve problems that we usually think of as requiring structured prediction. So it's an image object detection or classification. A decade or a half ago, people would be hand designing the features of the image later with this classification. Now, nobody does this. Everybody's building convolutional neural networks. We're doing this in which we learn very rich latent features of the image, but then in the end, make independent predictions among these things. And this is exactly what's done in problems like this. This is a 2015 paper that does object segmentation and detection. And look at the accuracy with which it's finding the umpire and the catcher and the batter here. And all this is done by independent prediction in the final layer, right after having gone through many and the same is true in this 2016 paper for pose estimation, in which we're estimating the joint angles in someone's body. Surely you would think this is a very structured prediction problem. But here again, these predictions being made layer to layer independently. One interesting facet of this model is that it has an hourglass shape through the middle. Actually, rather than this middle layer, it goes through many different layers of resolution, some of them very coarse-grained resolution that forces the model to bring information from many parts of the image together in one place. Maybe it forces some joint representation of input to facilitate this. However, not everything is rosy with this kind of approach. Here's a negative case in which we're trying to do natural language entity recognition, in which we receive as input a sequence of words, and we're trying to label them as people, organization, locations, or other. And we could consider a rich feed-forward model, like this LSTM, to build up some representation, which in the end makes independent predictions of each other. And this does okay, but not great. So this is a paper that was just presented 2 weeks ago at NACL, in which the LSTM that makes independent predictions does considerably worse than an LSTM that has conditional random field like direct dependencies on the labels at its top layer. So this leads me exactly to my next subchapter, doing deep feature encoding, but then making those features be the input into a graphical model to capture the dependencies of the labels directly. And rather than doing feed-forward inference, we'll now do energy-based inference like we always do with graphical models, meaning that inference is going to consist of a search over the values of the y's to find the y's that give the best image. So, rather than just predicting IID, we'll list the mad factors like this to capture the dependencies, and in this case, do return to do inference. in which this top part is just like a regular graphical model. It just happens to be that our representation of the input coming into the model doesn't come raw directly from the input, but it's some latent representation learned by default. And it's exactly a model like this that caused the revolution in speech recognition, in which rather than using what people were using before, various kinds of mixtures of Gaussians and other models, people use a deep neural network to build up representations of these frequency dynamics coming in from the voice, and then those become the observations in one of them. In this work, the neural network is trained independently for each time step. In other words, maturity is not used at training time for the neural network. And nonetheless, it works very well. However, in other cases, we can do better if we incorporate perturbing during the training of the neural network. This was done in this beautiful paper that was really ahead of its time in many ways. Graph transformer networks, in which we're trying to recognize some sequence of hand-drawn digits. Little image patches that can be input to a neural network, which can form scores on the edges of a lattice. We do viterbi on this lattice, both an unconstrained and a constrained to be the right answer of viterbi. And then backpropagation goes back, with the results of viterbi goes into fitting parameters of the neural network. So viterbi is used in training. In this case, maturity is run to completion before we do that backpropagation. Another variant is that we can interleave or blend the steps of leaf propagation and creating updates to the neural network, and it's going to speed up the training. It's taken from last year. So there's a lot of work in this area, and we can bring myself All right, we can also integrate inference and learning even more tightly through the following kind of method of insight. By unrolling the energy-based inference and doing backpropagation through inference. Let me describe it that. So here's our learning problem. Right? We've got some loss function, and we're trying to find the weights that minimize our loss. And if we're doing feed-forward learning, well, that's just a deterministic calculation of this function, which gives us the predicted y. But if we're doing energy-based learning with a graphical model, well, it's not feed-forward. It consists of some argument search to find the y's that minimize our energy. And if our model is complicated enough, then this argument is not exact. It's just an approximation. And this is just one of the approximations. As we're doing approximate inference, there's also this specified model structure and an approximate expected loss. And so maybe we shouldn't fool ourselves when we write down our loss by saying that we're really getting a true argument. We're not. We're getting the results of some approximate algorithm that gives us something. And so maybe what we should be doing is writing down our loss in terms of the algorithm that we're going to use at test time to actually do inference, which is just an approximation to our analysis, not a true analysis. And so when we do this, this will allow us at learning time to tune the parameters to the imperfect inference method that we're going to use at test time. This is always a good idea, right? To use that training, what we're going to use at test time to make sure we learn our parameters in the way that we'll do the best job. We can gain both speed and accuracy by doing this. And there are many inference algorithms that actually are differentiable computation graphs, meaning that we can use backprop through the steps of inference. And one example of a differentiable computation graph is actually leaf propagation. So let me describe that in practice. So here we're going to run deep learning forward to get some representation, but then up here we just have a graphical model, and we would be doing inference, say, by looping leaf propagation in this graphical model. What's that consist of? Right? We have some initial value for our y's, we do one step of leaf propagation to get an updated version of our y's, we do another round of leaf propagation to get the next values for our y's. And I'm now just going to redraw this in which I'm going to spread out vertically these different values of y, each step of leaf propagation. And I'm going to connect nodes such that whatever leaf propagation calculation I need to do to determine the value of this node, whatever the inputs to that step are, I have connections back to values of the earlier time step that I need to do that calculation. So these the computation happening from one layer to layer is exactly the computation of belief propagation. This is not a multi-layer perceptron, which is a matrix vector product. This is the computation of belief propagation from one step to the next. But all the computation of belief propagation is also differentiable. And so I can do back propagation through this graph. So this is sort of interesting. We're starting to blur the line between what does it mean to do feed-forward inference and to do some iterative procedure. Unroll our iterative procedure so it looks like feed-forward inference. And this lets us do various sort of wild things. We could also consider untying the parameters, which are weights across time, so that we have different parameters at different time steps of belief propagation. So perhaps in early steps of belief propagation, you have parameters that make faster, more wild, big leaps in space, and then later more refined, careful refinements of belief propagation. And what we find experimentally is that in comparison to doing training by back propagation through belief propagation, traditional training always loses. And so it's always better to do training by back propagation through belief propagation. And this is just one example of back propagation through inference, not just for belief propagation, but for mean field and other methods as well. People have also been considering computation graphs that do inference, but in which the graph doesn't really correspond to a graphical model inference algorithm at all. It's some inference procedure, but it just doesn't correspond to inference in any graphical model. And people have even been considering methods that are even more crazy than this. And let me take a moment to describe some work done by one of my students at Google this past summer. The problem is one in semantic parsing into complex queries, in which you're given as input a natural language question, like what's the sum of the numbers, the number of Olympic gold medals won by the US in years when the Olympics was held in Europe, and the Cold War was over. This is not actually a question. Yeah, it's task that represented an example. And so it's our task to, from this bit of natural language, to construct a structured program or structured query that can be run on a database or a set of tables in order to actually give us our final answer. And the construction of this structured program is done by a neural network that consumes these natural language words in sequence as input, and goes through a set of iterated steps in the neural network that one step at a time selects the instruction sent to an arithmetic logic unit that can perform the steps of this kind of program in order to get the final answer. And learning is done by enrolling the steps of this inference procedure in here. And it works quite well. And the amazing thing to me is that at training time, you're given just the original questions and the final answer, like 596, you're not given the program. And the program is latent, and yet it's still successfully trained. And recently, just a few weeks ago, it was posted to the archive, a paper in which inference builds up programs in the computer language forth. Programs that learn to do sorting and other things like this. These are nothing like graphical model inference. They're very different, and yet back propagation is working well for training. So there's work in this other area, these areas which are so I don't want to paint everything as rosy, though. To be realistic, there are some tough aspects here. It can sometimes be a bit inflexible in that often we use a fixed number of iterations at training time, iterations of inference, because we can't backpropagate the decision to terminate inference. That's a sharp decision. It can sometimes, there can be numeric issues in the optimization because normalization to a probability simplex yields vanishing gradients, and it also can be memory intensive because we're having to store all the intermediate steps of inference along the way as well. But nonetheless, there are many successful examples of this way. All right, so now this leads us to new work that I want to describe in the book we call structural prediction energy networks. So the motivations for our work are that we would like to simplify the model selection by breaking this chicken and egg problem by saying, well, rather than having to think very carefully about, well, which prediction algorithm do we need to use, we're going to talk about models in which gradient descent is always a good information on. We're also going to provide an alternative to graphical models, just to think out of the box if they're fun. But what I really want to emphasize here, the real underlying motivation here is that we want to use the power of deep learning to do structure learning, to learn about the structure of the dependencies among the variables that we want to predict. Right? We've shown how deep learning is incredibly good at learning very rich models of the co-occurrences among the input variables x. Well, what about co-occurrences among the output variables y? And this was a big intuition behind this. All right, okay, so we're going to slow down and coming up to the key slides that describe the whole idea. So here we have a deep learning neural network that's learning some representation of the input that becomes the input to our graph. And so this is just a transformation of the x's into something more convenient that may be more discriminative for solving the test. And this comes in as an input into a traditional graphical model in which we would do energy-based search in order to find the values of these lines. And that energy-based search is of course driven by this energy function. And how is that energy function calculated? Well, it comes from just the sum of the energies of each one of these factors. Right? These factors look at the values of their neighboring y's, produce some scalar value by sum together with scalars, and that is and this factor graph was designed by hand. It's relatively simple. It's just a linear sum of these things. Right? So we're going to do something a bit more rich. Right? We're going to replace the factor graph with something else that's also, in the end, going to produce a scalar energy. Get rid of the factor graph and replace it with what? With the deep neural network, which also, just like the factor graph, takes as input the values of the y's. And just like the factor graph, as output, uses a single scalar value, which will be the energy. If the bottom layer of the network comes in little convolutional patches like this, you can think about these bottom convolutional patches like the factors of the original factor graph. They're looking at just local neighborhoods of the y's. The upper layers of the network then are capturing the who knows what arbitrary, crazy dependencies you would never imagine putting in a graphical model. Right? Really rich co-occurrences, which we'll learn. How do we do this? We'll make some initial guess for our y. We'll feed forward to get the energy of that particular guess. We'll get a gradient from that energy. Let's say that learning is already done. I'll talk about learning later. At a test time, at inference time, we get a gradient on that energy. We do back propagation of that gradient through the network, not changing the weights of the network because those are already trained, but that gradient arrives all the way at the input of the network, at the y's, and the gradient is used to update the y's to values of y's that have that energy. That's one configuration. Then we'll feed forward again to get energy for the next configuration of y, again get the gradient, back propagate again, second value for the y's, and get it into convergence. Here, okay, the end of my first point. The second point is, notice that here the energy that comes from the representation of the x's has to pass through the value of the y's here. And so it's a relatively restricted representation of the input. Another variant we can do is to feed the representation of the input directly into this energy calculated function and do backpropagation through the entire thing. And what this means is that the representation of our dependencies among the y's has a very rich view of the x's themselves, and this gives us a natural way to do something very analogous to value-conditioned dependence, right? In which two parts of the y's may be dependent or not dependent, depending on certain values of our input. Right? This is something that's, I think it's a classic thing that's been discussed for years. There's the whole chapter in graphical or your Friedman's textbook on this, but in practice, nobody does it really. In my experience, because it's such a pain to set up. But here it just follows completely naturally. It just is handled exactly like we need. All right, let's get into some of the details. So in order to do gradient updates in the y's, if they had previously been, say, crisp binary values, we need to relax them into some continuous space, just like an integer. And then at the end, go round back to integer, so we get a final answer. This bottom part of the layer is the feature network. It's responsible for producing as output some vector representation of the input that we're being sent to learn to screen. This upper part of the network is the energy network. It takes our current guessed value of the y's, the representation of the inputs, and gives us a scalar energy. And what we're trying to do with inference is to try to find a smoothed y that minimizes this energy function. And we'll do that by taking the gradients of this energy function with respect to the y's. All right, so let's see, I'm going to lay this out visually what all the steps look like and abstract the details away so that I can make it a little bit smaller. So the gradients inside this energy function, and what does this look like? We take our inputs x, they go into the feature network. This is an inference test time, I'm not showing training right now. And you get some cached features. We won't need to calculate this again during the iterations of inference. These cached features will go into some initialization network that's used just once to give us our initial guess of what the y's might be. This is inference step number one. And then these y's plus the cached features are the argument to the energy function, which then gives us a scalar energy and also a gradient of this energy. That goes into some gradient step, which then updates the y's to give us a new value of the y's for our next step of inference. And then a copy of this energy network is then just run again on this new y here to again give us a new energy for the next y and gradient for another gradient step, a new value of y, and so on, and then repeat to so it may seem a little bit odd that this energy network, which is the key network we're talking about, takes the value that we're trying to predict ultimately as our output as the input here. And that may seem just a little bit strange, but it's actually not that uncommon. This Van Gogh style thing that I described earlier does the same thing. The original input, the original photograph is an input to this model, and this is also optimizing the energy using backpropagate all the way down to the raw pixels. Okay, so now let's talk about learning. I want to talk about two learning algorithms. The first is structured SVM, the learning in which the training loss looks like this. And it's a sum overall of our training data to find the worst violation of some incompatibility between the actual penalty and the model's energy difference. And each one of these looks at the true y should be from the label training data and the predicted y. And in order to find this max, we need to do some loss-augmented inference that looks like this. And unlike typical structured SVM, where this penalty function does not need to be differentiable, in our case, this must be differentiable because we're going to reduce this gradient descent in order to do the logarithmic inference. And then we reduce this cache gradient descent, and this whole loss function with respect to grades. The second algorithm is to do end-to-end backpropagation through inference, which I described in my third subchapter of the talk, in which we just take regular loss that we had before. And again, note that our predicted y's come from some iterated procedure that's calculated in a bargain, and acknowledge that that is an approximate bargain, not an exact bargain. It comes from some algorithm. And do direct risk minimization on this. So what is that algorithm? Well, it's one that starts with an initial guess for the y's, and then makes a bunch of, adds a bunch of gradient updates to this y's. Each one makes them local gradients in the energy with respect to y. And we can just take the entirety of this, which describes essentially exactly the steps of our inference algorithm, and differentiate the entire thing, and do backpropagation through all the steps of the inference algorithm. So we described earlier how to do backpropagation through one network here. Here, for learning algorithm 2, we're doing backpropagation through all the multiple steps of the inference. All right, so structured prediction energy networks are applicable to tasks with decomposable smooth loss functions, with relaxable labels, y, and with no hard-coded constraints between the labels through which we could not differentiate. So it's applicable to links in the social network, various graphical model problem, joint tables for close estimation, but not so much things like edges in a parse or a dependency tree. So a few technical details. When we cache the features for efficiency, we can progressively parallelize this into GPUs to make it fast. We can pre-train the feature network using an independent per label loss and use deep learning style optimization on the Ys in order to try to avoid local minima in our inference procedure. So there's various related work. The top two are examples of using gradient descent to change the input value to the neural network. There's recently been some work from CNU using spends but with energy functions that are convex and Y. There's also some work from the Berkeley Vision Group that uses a feed-forward network to predict changes to the Y itself and makes incremental steps of inference by using that feed-forward relation. So I'm going to talk to you, we're just in the early stages. There's a lot more work to be done. The experiments that we've done so far are all on the problem of multi-label classification. And we're given some input, and that's our job to predict the large bit vector of which labels should be present and which labels should be absent and classified on the circle. And so this is a widely relevant task, and the labels are often highly coordinated, but there's no given structure a priori, so structure learning is key. So the particular details of our experiments are the feature network is just a two-layer multi-layer perceptron. The energy network comes in two parts. One, a per-label linear model that takes as input the feature representation learned by the feature network, but otherwise it's just a linear classifier. And then a separate part of the energy network that captures correlations among the Ys. And I want to talk about this in a bit more detail. So this consists of taking all the Ys, projecting them into some latent space through the nonlinearity and that product. And so I want to note here that by projecting into a latent space that has much smaller dimensionality than the large set of Ys, we can capture high arity interactions without a blow up that's exponential in the labels, and that this measurement matrix here is often interpretable, which is a nice thing. I'll show you exactly that. So we ran this on 3 large data sets that have a very large number of labels, which is often competitive for doing, say, binary pairwise interactions CRFs for this kind of task. And we compare this on a large number of baselines, including some novel baselines that were quite tough. So if you just do regular per label logistic regression that captures no dependencies among the labels, or a version of logistic regression that also has some low break aspects like our models later. A feeds-forward neural network that does independent prediction in its last layer, but has a lot of structure in the middle. And also use quite a strong baseline deep mean field, by which I mean there are pairwise interactions amongst all of the labels, but we're going to train this by backpropagation through inference, backpropagating through the inference of the field, and then augmented spans. So we trounced other methods on this first 2 data sets. I think these are used to get our results. We came in second on this last data set, being beaten by the neural network. And one explanation for this is that in this data set in particular, the labels are less sparse, and precision recall trade-offs are more important, and logistic loss is better at calibrating those things against a threshold than the SPN loss. And running with our second training algorithm rather than the first would possibly help us. We also did some experiments with parsimony. So when we train using a large set of synthetic data, our model performed the best. But note that it's just the regular feed-forward neural network that captures a lot of correlations to the input did almost as well. So it's able to learn something about the correlation between the input just by learning enough about the raw input features and the correlations there. But if we have trained on less data, then the neural network does far less well. And those are very concerning about their accuracy. So it says something about our ability to maintain parsimony. And we also note that the measurement matrix in our model is very interpretable. It captures the kind of mutually exclusive structure that we expected. We might be wondering about convergence and how many up and down iterations through the network does it take for inference to converge. And
In our experiments, most of the things converged in about 20 innovations, but there were often a few stragglers. We hypothesized that, that many of these difficult inference cases were cases that we were going to get wrong anyway. They were just tough cases in which we weren't going to be making correct predictions. And so we found that we could essentially just give up on these tough cases early and hardly lose any accuracy at all. So it's available. All right, so there's a lot of other work in multi-label classification we could do about later. And so now I want to wrap up. So we were looking earlier at the trade-offs between doing feed-forward prediction, the kind of dependencies that can be captured there versus energy-based prediction, whether it be with graphical models directly or the kind of structured prediction energy networks that we really have. So it's easier to do inference with feed-forward prediction. We argue that it's easier to inject domain knowledge, it's easier to interpret, and it's more parsimonious to capture dependency between the lies together. And so these kinds of models are important for small training. And you might think, well, but how often does this happen? Well, the neural network philosophy is that we should always strive to be in the small training data regime by saying that we should be increasing model capacity until we are. So we should build massive capacity models that really are able to capture full fine-grained details of our data. Squeeze as much use out of it as we can, and then that puts us in a small data regime in which these considerations are important. So some future directions. I think it's interesting to, we saw how the measurement matrix here was interpretable. It's interesting to consider exploratory structured learning by doing deep learning. There's been a lot of success in the combination of deep learning and reinforcement learning, and we can consider cases in which the action space of reinforcement learning actually has multiple facets with some structure between them all at the same time. We can also consider cases where the latent space is structured. If you want to capture dependencies amongst the multiple variables in some intermediate link space, like in the neural programmer question answering task that I talked about. I said nothing about causal learning here, and that's another rich area to consider. I particularly having insights into what could be done, but I think it's interesting correctly. I think it's also interesting to consider very large structured data, like entire knowledge graphs the size of Google's freebase, or knowledge graph. And one thing I want to note especially strongly is that a big part of the success of deep learning is that there exists various excellent software packages for building large deep neural networks conveniently, and that none of these integrate the ability to do structured prediction, like graphical models or energy-based inference into them. Very interesting to build models for vehicles. All right, so I'm done for now. I want to open things up for questions, and this has me thinking about my father, who, when I was a young boy, always encouraged me to think out of the box and to ask questions. And he just passed away a little more than a week ago, and so now it's up to me to encourage you to ask questions. And so with that in mind, I'd like to open it up. Thank you very much.